No worries. All right, let's make a start. So the agenda for this class is to go a bit further into fundamentals of transformations. So we're now looking at how to determine a sequence of transformations. Rather than having the transformation already and applying it, we're now going in the opposite direction. So for the bulk of this, we'll work out of the screen share. For the first half of the lecture portion, we'll continue using that point form notation that we used in the previous class. I do also have written examples of if you want to use function notation instead. I know some of you have different preferences around which way to use it. I've personally found that most students find this first section to be easiest to follow, this first sequence to be easiest to follow, but I've got both in there just to cater to wherever you're currently at. So these are all the steps. That's just a whole bunch of blue text. So let's just have a look at what that actually means in an example. So here's the kind of question that we're working towards. We're trying to figure out how do we go from a transformed state to an untransformed state. So the question reads as follows: find a sequence of transformations which maps the function of f to the function of g. That's the whole goal, right? What transformations have to be applied to this to make it look like that. That's actually the first step of our process. Figure out where are we starting and where are we going. What is the original function, f, and what is the new function, g? We're mapping f to g, so we're starting from f and we're ending at g. This is important not just for your own understanding of the question, but also for the notation that you use, because what you'll do is you'll use x and y notation for the starting function, and you'll use x dash and y dash notation for the final function. So here's what that looks like. F is going to be rewritten like this. Nothing really changes except for the y at the front. G is a bit more drastic. G is going to get y dash, and this x is going to get x dash down here. In that way, we now figure out where we're starting and where we're going. We can rearrange for the correct terms, which is what we're going to be doing here. Rearrange all the transformation factors affecting y. They're going to stay on or go to the y side, or the left usually. And the transformations that are affecting the x are going to stay on the x, or on the right-hand side. So if we look at f of x, the original function, there's a few transformations that affect the y. One is a vertical translation, +6. The other is a dilate factor of 3. And so what we're going to do is put those to the other side. Subtract 6, divide 3. We have all the y stuff on the y side, all the x stuff on the x side. For those who have trouble figuring out what's an x and what's a y factor, the hack around that is just rearrange as much of this as you can without messing around with what the actual function type is. Like if you try to do anything else to this, you'll break it down from being a truncus. It won't be a truncus anymore. Like you'd have to square root, you would have to expand this out, anything like that breaks the function into something that's not a truncus anymore. And so that's your indicator on when to stop. Otherwise, keep going, move everything over. Any questions on how this works so far? I'll pause for a minute. Okay. We're also going to do that for the other function, by the way. It just so happens that there are no transformation functions on that, or transformation factors on that, and so we leave that as is. So we're going to end up with two final expressions, one with the new f and the other with the new g. From there, what we're going to do is compare the two components to each other. The x components are going to be equated and the y components are going to be equated. What does that mean? Well, here's the y component of the first one. It's the entire left-hand side. Here's the y component of the second one. So you put an equal sign between those two things. This equals. Same thing over here. Here's the x component of the first one. It's that horizontal translation of 1. Here's the x component of the second. Just x, or x dash. And so we put an equal sign between those. Now, if you have trouble figuring out what on the right-hand side do I take and what do I not take? Just take the whole thing. It's totally fine if you want to take the entire thing and rearrange from there. It still works out just fine. So I'll go to the handwritten section now and show you what happens if you do that. You'll still be able to get back to where I got. It just takes a few more lines of working. So if we have 1 over x minus 1 all squared, if you just take the two right-hand sides together, 1 over x dash squared, you can multiply both sides by x dash squared. You can multiply both sides by x minus 1 all squared. That's a bit blurry. Is it gonna... Please? There we go. Cross multiply in that way. You're going to have x dash squared equals x minus 1 all squared. And then finally, you square root both sides. X dash equals x minus 1. You get back to where you would have gotten if you were able to identify the actual transformation factor first. So this is a fallback strategy. If you forget what you're doing, just grab the entire right-hand side. Okay, from there, once we have that, rearrange to get x dash and y dash on their own. Good news is, in this case, they're already on their own. The reason we want x dash and y dash is because we're trying to figure out what the transformation is. And if you remember in the previous lecture, or for those of us who are new, x dash and y dash are the actual transformations that are applied to make a certain thing happen. That's why I want x dash and y dash. Not every circumstance will have those on its own. In this case it does, so we're happy. Which means that we can write out our expression. We have xy is the same thing as x minus 1. That's our x dash, and y minus 6 over 3. That's our y dash. xy maps to this new transform state. Under some circumstances, that's where you can leave the final answer. If it just says do it in the xy notation, that's what you give as a final answer. Most of the cases, you have to write it in words. This is where it gets somewhat challenging, because when you're doing this kind of approach, one thing to consider is that the order in which you say things matters a lot. The other thing to consider is the way that you've expressed this answer changes the order you say the words in. If you do what I do here and factorize things out, so I'm taking a common factor of a third out of the... It's not really a common factor, it's more just bringing this out the front, but you get what I mean. It's already factorized, just rewritten in a different way. If you have it in a factorized form, you do translations, then reflections, then dilations. You do it in that order. Most schools will teach DRT, dilate, reflect, translate. We'll look at when you would do that instead. But for now, if you have it in this form where everything is factorized, then you do translations first, then reflections, then dilations. So this here means a shift left by 1, or you can read that for the more mathy terminology. Then you got a shift down by 6, that's that one. And then you got a dilate factor of a third along the y. You could also say from the x in that situation. This is probably the best way to do it. Just do all the translations, then all the reflections, then all the dilations. Technically speaking, there's a bit more freedom. The x and y are independent. So you could do all the y first, then all the x, if you wanted to. So you could do the translate, dilate of the y, and then the translate of the x. That's another way of doing it. That just makes it more complicated though, so if you're learning this for the first time, or this has been a tough bit, just do this sequence and then look across both. That'll be more than enough. Where you would use DRT instead is if you don't factorize but expand instead. So I'll come through and do that now. So if you've already learned DRT, then what I would say is do this instead. So you have x goes to x minus 1, and then you're going to have y goes to a third y minus 2. You're going to expand that coefficient of a third through everything. When both things are expanded, Then you do dilate, reflect, translate. So if you've already known to do things in DRT, this is what you want yours to look like. If you don't have a preference either way, then pick either what you see on the screen or what you see on the notes. It's purely up to you. Anything to clarify there? I'll pause for a moment. Okay, that's that. This is another example here. I won't go through the whole thing because it's basically the same. The only reason it's in here is to show you that it doesn't actually matter where you start and where you end, as long as you know what the start and what the end is. The exact same sequence of things will work. So in this case, we're going from an untransformed x squared to a transformed g of x. We're still going to follow the steps as normal. The only thing I'll point out here is that this is one of those cases where you do have to now rearrange for the x dash y dash, because currently they are trapped inside the terms, inside the expression. So that's the only thing I wanted to highlight. You might have to do that. Otherwise, yeah, follow the same stuff. Here is the other approach. So if you like working with function notation, the advantage there is that this is faster. Doing it this way is much faster. The disadvantage is that personally I find a lot more students will make more mistakes doing this. So try both. If you're really interested in doing really well, then this will be the thing you probably choose because you'll practice it enough to where you stop making mistakes. If you find that method's a bit challenging, you probably want to stick with that first method. What I've noticed is that I can't necessarily give step-by-step instructions here. I can more so give guidelines here. It's much more of a free-form sort of thing you have to do to solve it. So some of the guidelines include making sure both functions are actually in their general form. You want to be able to see what all those transformation factors are. Like if this was expanded, you would have no idea where the turning point is unless you try to solve it. Get it to a completed square form in the case of quadratics, or in the case of anything else. Just make sure you can see what's horizontal, what's vertical, what's dilates, what's reflects. As long as you know that for both functions, you'll be in a good state. This one here, more of a reminder, y is independent to x. So when you're doing your manipulations, anything that affects the y is not going to touch anything x related. Anything that touches x is not going to touch anything y. So you have a bit of freedom in choosing. You'll see later what that looks like. And my preference would be to do your transformations in order of DRT when you're actually applying them, and you'll see why in a moment. So this example is pretty chill up here. Going from F to G, you can see the only difference there is a shift right by 2. So you don't have to go through all of this nonsense to figure out, yeah, I'm just going right by 2. Like, there's nothing too crazy about that. It's more so a bit more challenging now to use it when you have a lot more things going on. But let's see how we go. First things first, this I know everything about, this I know nothing about. So let's rewrite G to be something that's a bit easier to keep track of by completing the square. So this is just me completing the square. If you need to revise that, then there's plenty of notes around here to do so. This is just completing the square. Reminder, that's cool. Next up, we're going to apply transformations to F to make it look more like G. And because they're both in this form now, it becomes a bit more obvious how we can make F look more like G. For instance, if we're looking at dilates first, like we should be, we're starting at a dilate of 3, we want a dilate of 4. So if we want to go from 3 to 4, we need to figure out what do I need to multiply F by to make it look like it has a coefficient of 4 at the front. This is how we do that. So to match them, you simply got to figure out what multiplier do I use. And in this case, if you multiply 4/3, so you put a division of, I'll restate that. The easiest way to change the coefficient at the front is to first kill it which means divide by whatever that number is, and then multiply by whatever number you want it to be. So if you divide 3 by 3, you get it to 1. Then from there you can make it look like anything, like let's say 4, by multiplying by 4, which is what we're doing here. Dividing by 3, multiplying by 4. Just remember that because we had this vertical translation up here, this is a y thing. Yeah, it's vertical. So when you multiply everything by 4/3, you'll fix up the dilate factor just like what you want. But what you'll do is you'll change the vertical translation. This is why we do dilates first. Because if you do a translate first and then you do a dilate, your translate gets ruined because you've now multiplied it by another number. So you have to go back and do it again. So save yourself the hassle, do your multiplies first. The other thing to notice, nothing in the x changed. It's nice and safe in there. We did a multiply on the y, all this x stuff didn't change. From there, we've done all the dilates we need. There are no dilates in here we need to worry about. Next up will be reflections. Nothing. If you compare the two, there's no negative signs in there, or at least no negative signs on the outside or on the x, so we don't have to worry about that. Nor should we ever, really. I mean, only if it was negative out the front. On a quadratic, it's not going to have negatives in here. It wouldn't actually do anything. But that's besides the point. Finally, we'll do some translates. So, to get from F to G in the vertical direction, you just want to figure out what do I need to add or subtract to this to make it look like 12. And so you literally just do the subtraction between them and you'll figure out what the difference is and just add that. If you add 8/3 to this, you'll make 36/3, which of course becomes 12. That's going to make the plus 12 look like the plus 12 from G. So you can see that they're pretty damn close now if you compare F and G. Only thing different is that this is a -1, this is a -2. We've done all the Y stuff, now we can move on to the X stuff. So how do we get from -2 to -2 to -1? Well, +1 on the inside. That'll be a shift left by 1. Just like that, we've got F looking exactly like G. So all we have to do is keep track of what we did at each stage. The first thing we did was a dilate by 4/3. The second thing we did was a translate up by 8/3. And the last thing we did was a translate 1 left. All we're going to do is write it in order of what we just did. Any questions about how that method works? While you think about that, I will grab up the prescribed work for today. I think I got the right one there. Textbook questions. Yes. Okay, cool. So in the chat there, you'll see that we have, it's a Word doc that will tell you basically what chapter we're doing in the textbook for this particular topic. It's going to be 7D. And if you're already pretty skilled at 7D, you've also got the chapter review as well, chapter 7. Both are detailed there. If you don't have the Unit 1 and 2 book, and I do specify this is the Unit 1 and 2 book, make sure you got the right one. It's in the Google Drive, right? So there's a Google Drive on the notes of that Word doc. You just click the link, download the book, and it'll be sorted from there. What we do from here, for those of us who are new, is we go into breakout rooms now. So what's going to happen is everyone's going to have their own breakout room. I'm going to circle around and see how people are doing. We'll work 5 or 10 minutes each together. And yeah, I'll help you out with anything you're either doing now in this class, or if you wanted to bring anything to this that you're working on in your own schooling, then I'm happy to look at that as well. Okay, so if there's any questions, let me know. Otherwise, I'll set up everyone's breakout rooms.